Hello everyone. My name is Gaëtan Colette and my colleague is Yannis Gharbi. And we're going to present you the work we've done with the third colleague, Christophe Langenbronn, who is in the public today, about the development of new feature in Codaster to support safety analysis at Framatome. So in the first part, we're going to talk about the partnership we have around Codaster. Then we will go into the detail in the finite element industrialization process, what we have done for the user. Then we'll talk about the result extraction for safety analysis, and then we will conclude. So who we are? We come from the Burgundy Calculation Center within Framatome. It's an entity of the Mechanical Engineering Division. We are located in Saint-Marcel, next to the historic site of the factory site. And we also have offices in Lyon. And we are a team of 100 of engineers and technicians working on the mechanical calculation. What we do, so we are mainly working on stress reports and fracture analysis reports for heavy equipment, steam generator, reactor pressure vessel, pressurizer, and primary piping. We are also working on the mechanical integrity for equipment on site for handling or lifting stuff. We have also activities in the defense area. We also support for piping and piping analysis and also on-site mechanical integrity on-site. And the main points here is that we are responsible of the development and maintenance of mechanical simulation codes. And also we are providing training sessions for our engineer and including a Codaster and Salomeca training module. So about the history of Codaster at Framatome and our partnership. So we have started working with Codaster in 2021. So now it's one of the key reference tools for finite elements at Framatome. Also, we have done some work, some developments to industrialize all the study stages for our user to make it more user-friendly for our application. We also have done the validation of the version 16 of Codaster with our own industrial test cases. So it was done in 2024. And a specific point is that we have some know-how method that we want to keep as intellectual property, so we can't share it as an open source feature. So we have two types of developments that we are doing. In 2025, we have signed a partnership agreement with EDF R&D to define what is going to be an open source development and what will be kept as an intellectual property. And this contract, we are updating it with our new development. Also, we are following the quality assurance of EDF R&D. So for each new features that we want to push into the code, so we use EDF tools, and it's tracked in the GitLab and in the Rex issue, the system of EDF. We also participate in convergence meetings to talk about what we want to do and how to do it. And also we are following the continuous integration. Now about the finite element industrialization. First of all, I'm going to make a quick introduction to a specific method that we are using. The name is the transfer function method, and it helps Framatome to do a lot of thermomechanical, to have a lot of thermomechanical answer to some transient, to some description of temperature evolution, but with a few number of actual simulation, actual finite element simulation. So if you have a system with two areas where you want to apply two different temperatures, and you know the description of the evolution of your temperature, you can apply on each area a 1 degree unitary shock while you're maintaining 0 degree on the other area, then if you compute the thermomechanical response to this unitary shock and the derivative of it. So if you have it, when you know the real description of temperatures that you want to know, you can obtain it with the convolution product. So in this example, there is only 2 areas, but if you have, for example, 10 areas, you just need 2 finite element computation for each area, and you can have hundreds of thermomechanical response. The hypothesis behind it is that it only works if it's in linear elasticity. So, for example, the number of transients we are interested in Framatome in our studies, it can go up to 200. So it's a lot of gain in time and in resources. For this specific method, we need to perform multiple thermal and thermomechanical simulation. So we have 2 simulations for each areas. And for the user, it was a bit of a limitation because we have to repeat the same operation a lot of time. So with the thermal and the thermomechanical for each area. And that's making a lot of results to handle because each simulation is for one area and it's one result that you have to keep track of, one concept. And also for thermomechanical analysis, you have to define a new material with a new variable, a command variable, each time you want to do the calculation. And also, because of the specific method where you want to apply 1 degree somewhere and 0 degree on all the other area, you have to be careful and not make mistakes to forget one area. And so for the user, it's a lot of combination of loading to be sure of. We have developed a command named calctermult, which is already available in the 17 version, which allows to, with common thermal boundary condition, you can define different load case where you're just giving the thermal loading you want for each case, and it's only one command. And in the end, you have a result, one concept, which is like a Python dictionary. So it's a result where you can go and access each load cases by a key, by the name of the load cases. So it's more convenient for the user to handle only one result than a lot of them. And also for our application, there is a simplified way of applying a unitary shock on each area, and the command automatically applies 0 on the other area for this specific application. Also, so that's what is already available in Codaster. And what we are working at the moment is, so sometimes we are modeling an heterogeneous material which, for example, contains thousands of holes with tubes, and we want to model it only with an homogeneous equivalent material. But we need to take into account the exchange between the fluid that can go through the holes and the sheet, the metal sheet. And there is a specific way of doing it. It's by using different source terms to diffuse some heat inside the system. And we want to make it simpler by a specific keyword in this command instead of defining a lot of loads. And all of this has been made as a Python macro command. So it's quite easy, let's say, for someone who knows Python to implement this command. Another development that we have made, it's similar in a way to what I have just presented. It's a calc-mechamult, and it allows to do the resolution of multiple thermomechanical simulation at once. So in this way, you just give at the command the common boundary condition for all your cases, and for each keyword for each cases, you just give the thermal evolution from which you want the thermomechanical answer. So with one command, you can have 10 thermomechanical answers to the same mechanical problem, but with 10 different temperature fields. Also, if you give directly the concept that is the result of calc-termult, so the concept already contains, let's say, 10 load cases, it will automatically give the thermomechanical response to the 10 load cases. And it will keep track of the names, and you will have one result dictionary at the end as a result. So this is also available in the 6.17 version. And what we are working on at the moment is to extend this command to mechanical-only load, so to be an alternative to what already exists in macro LS-mult, but the result would be a dictionary in the same way. So you can have in the same concept mechanical answer, thermomechanical answer, and with no limited number of results. And also you have the same format for both of them, because macro LS-mult at the moment doesn't work this way. We also have made a small development to adapt the output of macro LS-mult, because when you want to print a result from macro LS-mult, it's sorted by the order, order number of the results. For example, your first result will be at the order 1 and the second at the order 2, but it will be considered as one result with different order number. And we have done this work to be able to have different results, all the results for all our cases. And also, we have modified improresu to be able to print a result from calc-termult and calc-mechamult.
So now I will talk you about how we choose the time steps inside the thermal unique shock that Gaëtan told you before. These time steps are computed thanks to an external Codaster command, but it looks like a real Codaster command. This command is called ter instant coupe, and it's a Framatome IP. So here on the right, you have an extraction of a COM file that uses ter instant coupe. Here, in order to use this command, you have to import the command before, because Codaster doesn't know the existence of this command. But when you import it and you use it, it acts exactly like a real Codaster command. Here in the mess, you can see that the command is numerated as a real command. The outputs are given here. And the advantage of doing that is that we use an external catalog that can check the syntax exactly the same as it could be done for an actual Codaster command. And inside this command, we do thermal and thermomechanical computation with Codaster on 1D lines in order to adapt the time stepping and have an adapted one. Now we will go to no more on the thermomechanicals, but on the mechanics, fully mechanics computation. We've noticed that in Codaster, put a force, a torsor, it's a French word for a torque and a force. When we want to put that on a face, it could be quite complicated with Codaster. You have to modify the mesh by adding a node or a beam in order to couple it with the surface you want on which you want to apply the force. And it's quite complicated to use a local referential, and you cannot use finite strain, and there is no lever arm correction when you use an overlength in order to not consider the border effects. We will introduce in 18th version of Cadaster a new keyword in Afecharmeca that allows to limit to use this functionality. You can put the forces in the local coordinate system, and the resultant, so the forces are made from a local pressure. That the formulas are given here, and they are represented on these figures. So here is for a torque, and here for a bending moment. On the right, you have the syntax of the command. And we can say on this development that it was not so complicated. This was our first real development in the Fortran of Cadaster, so for us. Thanks to the support of EDF, they clarified to us how to do it. The elementary computation of the skin elements are very accessible, readable, I thought. And the Fortran of Cadaster, it's not so complicated, excepting when you have to deal with the memory manager. So the last subject is the result extraction for our safety analysis. Our safety analyses are based on extraction on 1D lines that we will call path lines. So our need is to extract result on these unidimensional lines, and we have to be sure that the extremities of the lines are on the skin of the mesh. So in order to do that, we've introduced in Cadaster version 17 two commands, crea coupe and extra coupe. The first one is necessary for computing the intersection between line and the skin of the mesh. It's a macro command in Python, but Python interface of Fortran function has been done. So we made the interface between Fortran, C, C++, and Python. The second command actually do the real extraction on the path made in the previous command. It's a macro command too that uses proche-champ, maudit repère, and so on, and it defines a result format adapted to passes. The mesh is defined on sec2 edges. There is a group of nodes in, nodes out, and each pass line is in a group. And for other things, we use met coupling and post-roll VT to do stuff with the fields. And for defining all that into a graphical interface, we are developing a graphical interface called Camino. It is an ergonomic platform to generate pass lines, and it allows us to accelerating the creation of passes, because in our studies we can have many passes, and it could be complicated to create all that stuff. A first version is expected in 2027. Another development we've made internally in Framatome is the fact that we have old codes that using results from other finite elements. So we've done three things. The one is the first one is the thing illustrated on the scheme here. It's a unified library allowing us to read med file and other finite element pass file with an interface in Python, C++, and Fortran that allows us to couple the new results with our old legacy codes. And we develop a tool. Second point is the development of a new tool for combining all our unitary shock with the transfer function methodologies. So it's the first slide that Gaëtan presented you before. And in another post-processing tool that we have for fatigue analysis, we use MED directly to read our RMED files, and it works and it is used in industrial studies. And for conclusion, the collaboration we've made with EDF is really successful, thanks to regular exchanges and interaction, and our contractual network framework. Then the development in Codaster allows us to carry out our studies. The development of new features from an external company is quite not so complicated. Thanks to our library, external tools can be interfaced easily. And we can use Codaster in regulatory studies, and we are still working on developments for version 18. Thank you for your attention.